Welcome back to my favorite universe. Today, the subject is one of the most fascinating in all the cosmos. Today we're going to talk about black holes. And just as by way of statistics, when I'm out in the public and people know that I'm an astrophysicist, it's one of the top 3 questions I get asked. Usually I get asked something about the search for life in the universe. Next is about the Big Bang. Third, right up there with those 2, is what is a black hole? Are they dangerous? What will it do to me if I run into one? Well, first, yes, they are dangerous. They will kill you post-haste. And they're also extremely fascinating because they wreak havoc on the environment in which we find them. I've titled this lecture Death by Black Hole because while we can first describe how a black hole would kill a person, that's fascinating unto itself. But this havoc that gets wrought upon the environment by black holes throughout the galaxy and throughout the universe, in a way, is killing stars and gas clouds. And so it's really just a lecture about death and destruction caused by black holes. For human beings, it's quite a spectacular way to die. If I were to choose a way to go, I'd say launch me into a black hole. Because what it does is it rips you apart atom by atom, and you go in as a stream of matter right down to this bottomless abyss. And we'll detail that a little more in just a moment. But first of all, what is a black hole? Let's start at the beginning. What is a black hole? A black hole is a region of space within which the escape velocity has exceeded the speed of light. And the escape velocity is a magic speed with which if an object were launched at that speed, it would escape the object forever. It makes sense that for higher gravity objects, they have very high escape velocities. But for a black hole, that escape velocity is the speed of light. And you know, the speed of light is the fastest stuff we know of in the whole universe. So if light can't get out, nothing gets out. Nothing. Hence the name, black hole. It's black because nothing comes out. It's a hole because if you fall in, you're gone. Sensibly identified. Now, what this business about escape velocity, let me give you a sort of grassroots discussion of escape velocity. I'll use my shoe for this demo, if you don't mind. If I take my shoe and toss it up, I play catch with myself. I toss it up. It goes up about a foot and comes back. I threw it at a particular speed in order to reach 1 foot above my head. But if I threw it at a higher speed, it goes even higher. It takes longer for it to return to me. If I keep doing this, constantly increasing its speed, I can do the experiment and find out at what speed will the shoe never come back. If you do that experiment, you'll find that that speed is about 7 miles per second. Converted in speed limit language, it's 25,000 miles per hour. Extremely fast. You don't encounter this in everyday life. And that's probably what led to the adage, what goes up must come down. But that adage is more just from some everyday experience. If you look at the physics of the cosmos, there is a speed with which you can launch something so that it'll never come back, rendering that childhood remembered phrase incorrect. You might go back and tell your teachers that. So it makes sense that the escape velocity must somehow be correlated with how much gravity there is on the object from which you're launching, on the orb from which you're launching your object. Let's take a very low mass thing like a comet. Comets are small. A big comet might be 100 miles across. The escape velocity on a comet is about 1 meter per second. You can calculate that out. That's about 2 miles an hour. You can walk that. A brisk walk is 3 miles an hour. So if you ever found yourself on a comet and just started walking fast, watch out, because you'll just sort of you'll propel yourself into orbit around the comet. And by the way, that's why comets are very dirty things in the solar system. Anything gets jostled loose on it, it flies away and the comet loses it. It's this big garbage heap, and it strews garbage behind it every time it comes around the sun. In fact, that's the cause of meteor showers. Earth plows through the debris of these things, and it rains down on Earth's surface. It's because it has a low escape velocity. But what's next? We can go to the moon. The moon has more mass and more gravity than a comet. For the moon, the escape velocity is about 2.5 kilometers per second. That's relatively fast. That's fast. That's about what is that, 1.5 miles per second. I can't throw anything that fast. You need launch vehicles to do that, even on the moon. NASA did that, of course. We landed on the moon and then escaped back out of the moon. They had to be launched from the moon at that speed, otherwise they would have fallen back to the moon. Let's keep going. As we know, Earth, 25,000 miles per hour. The sun, escape velocity is about a little more than 600 kilometers per second. About 400 miles per second. That's fast. That's really, really fast. It's very hard for things to just sort of escape the solar system because the sun has this near eternal lock upon them because of such a high escape velocity. But what it means is, what that number means is if you're standing on the surface of the sun and you want to say, goodbye solar system, if you don't have that speed, you're going to fall right back to the sun from whence you came. Now, yes, mass matters. High mass objects generally have high gravity, but size matters too. Size matters too. The more compressed an object is, the closer you can get to its center, the closer the surface of that object is to its center. And the force of gravity is related not only to the mass, but what is your distance to the center. That is the force of gravity. And so black holes and other dense objects in the cosmos, they might not even have that much mass. A black hole might have the mass a few times the mass of the sun. There are plenty of stars with that mass. But it's because the black hole is small that its surface gravity is high and the escape velocity is high. And it can plunge down in, close back on itself, preventing light from escaping because its escape velocity has exceeded the speed of light. Now, this region of space, we think of it as a surface, but it's not a solid thing. It just happens to be within which you don't come out. It's the point of no return. We have a word for that, this point of no return, rather poetically described as the event horizon. The event horizon of a black hole. Now, you might ask, where did all this come from? Did we just make this stuff up? No. Someone you've heard of before, Albert Einstein, when he introduced the theory of relativity back at the turn of the century, 1905, that was special theory of relativity concerning motion in straight lines, non-accelerating motion. And then 10 years later, 1915, published in 1916, he came up with the general theory of relativity, which described motion of any kind, accelerated motion, including gravity and the acceleration of gravity. That is known as Einstein's general theory of relativity. And in that, he described the force of gravity not purely as a force of attraction between two objects. That's very Newtonian. Newton's theory of gravity thinks of attractions in that way. What Einstein did was said, no, gravity curves space. And when objects move, they are moving in response to that curved fabric of the universe. And there's something called an embedding diagram, which indicates this for a black hole. Here we have, imagine space, we live in 3 dimensions plus a dimension of time, that gives us 4, and it's hard to imagine that warping. So let's, by the way, we would be able to see it if we were higher dimensional creatures looking down on the space in which we live. So let's do that, but for our case, let's create a 2-dimensional universe, this sheet of rubber with a grid on it. And let us warp that sheet of rubber. So we're living inside that sheet of rubber, and there's the warp that we're talking about. That is the kind of warp that exists, except in higher dimensions in the universe we live as described by Einstein. But here, because of our feeble human minds, we can only imagine it in the 2-dimensional case. Notice the warping of space. So at the center of that funnel is an object of very high gravity. And if it's a black hole, that funnel is so long you're never climbing out of that to escape back into the grid of the rest of the cosmos. So that's a way to think about what's going on. By the way, if there were 2 objects in orbit around each other, you'd have 2 dimples. Imagine a cluster of stars. There'd be dimples all over, all responding to their own distortions of space and of time. I'll add that There's a phrase, I first heard it from John Archibald Wheeler, who was a student of Albert Einstein, summarizing all of general relativity. And he said, matter tells space how to curve, space tells matter how to move. And for me, that summarized all of the philosophical underpinnings of the theory of general relativity. Now, why would something collapse down into a black hole in the first place? Well, it turns out usually things are supported from collapsing under gravity. They could be chemical forces, it could be thermal forces, the movement of molecules. Gravity's trying to squeeze it down, but they're moving fast, and so it prevents it from collapsing. So those are forces, but if you have so much mass, you can actually overcome that and cram matter down until it's sort of atom next to atom. That's possible. You can do that. We have states of matter that are just that. We call them white dwarfs. Then you can cram it down even more until it's not just cheek to cheek, atom to atom, but it's nucleus to nucleus. If you do that, you get a neutron star. That's the densest matter we know. Neutron stars, if they're rapidly rotating and we see them that way, we would label them as pulsars. Now, what happens if it has so much gravity that this pressure of neutrons can't even support against them? That's all she wrote. We know of no force of nature that can support an object against the gravitational forces of, let's say, a ball of mass, 5, 6, 10 times the mass of the sun. Once that starts making its nuclear fuel and it begins to collapse, nothing is left available to support it against the collapse. And the matter just keeps going and it descends through its own event horizon. That's when it disappears from view. And as far as we know, all of the mass collapses down to a single point of infinite density, zero volume. Now, that's kind of absurd. What does that even mean, infinite density? I don't know what that means. But what I do know is that general relativity, the most successful theory of gravity ever put forth, fails at that singularity. So we know that it's a theory that is incomplete. Even though everything it has predicted has been true, it's an incomplete theory, and we're searching. String theory is one of them, one of the ideas put forth that'll give us a handle on the singularity deep inside. But it's for all these reasons that black holes are some of the most romanticized of cosmic objects. They're mystery, they're mysterious, they're dangerous, and they're basically fertile for storytelling, particularly in the realm of science fiction. So, why don't we take a feet-first dive? Why don't we take a feet-first dive into a black hole and see what happens? Well, as I'd already mentioned, as you're descending towards the black hole, the force of gravity is growing exponentially. But all that means is you fall faster. And if you're in free fall, you're actually weightless. So you wouldn't care that you're descending towards a black hole because you wouldn't notice it just yet. You'll just be falling. It'd be like falling towards Earth or falling towards anything. So that's not what kills you. It's not the high gravity that kills you. You know what it is? It's the difference in gravity between your feet, which is closer to the black hole, than your head. There's a difference in gravity as I stand here on Earth between my feet and my head. I barely notice it because my height is very small compared with the radius of Earth. You can ask, how much stronger is the gravity at my feet than at my head? Well, look at the size of Earth and look at my height. It's basically nothing. So I don't even notice that difference. But if you're descending towards a black hole, and black holes can be tiny things, if the size of the black hole and your height are comparable, imagine in a limiting case, I've got a 6-foot diameter black hole, and I'm about 6 feet. I'm like falling towards the black hole. My feet are twice as close to the black hole as my head. You calculate what force that is. That my feet are feeling an acceleration towards the black hole that's 4 times the acceleration of my head. I begin to stretch. My body begins to feel like something is, like I'm on a rack. Now, if I were made of rubber, of course, a rubber man, I would just stretch according to these forces. But I'm not made of rubber. I'm made of human flesh. And that has force limits. By the way, these forces, this force that stretches you as you descend towards a black hole, we have a word for it. It's called tidal forces. It's the same word as in the tides on Earth. Earth feels tides from the tidal force of the moon. One side of the Earth is closer to the moon than the other in a measurable way. And so the oceans feel a little bold. They're drawn a little more on the near side of the Earth than on the far side of the Earth, so that there's this stretching of the oceans in response to the tidal forces of the moon. Now, if the moon can do that to Earth, imagine what a black hole can do. So what happens? I begin to descend, and eventually these tidal forces exceed the chemical bonds of human tissue. And as I descend, there's a point where I can no longer resist it. And I snap into 2 pieces, a lower segment and an upper segment. And I keep falling, and then, sure enough, those 2 segments feel enough of a tidal force that they snap into 2 pieces. And then those 4 pieces each snap into 2 pieces. And it goes from 1 to 2 to 4 to 8 to 16, and this just continues. Eventually, you are completely snapped into countless pieces of biological matter as you descend towards the black hole. Now, it gets worse than that. It turns out space and time have collapsed onto a black hole. This is what general relativity describes for us. It squeezes down into the black hole. And so here I am occupying a space that is in fact getting narrower and narrower and narrower, like a funnel. So not only am I stretched head to toe, I am squeezed shoulder to shoulder. It's as though my body is being extruded. I think of it's like toothpaste being extruded through the hole in a toothpaste tube. That's what's going on as you fall towards a black hole. It's also like, I don't know if you've ever had one of these homemade spaghetti making machines. You take the semolina dough and you knead it and put it up and put it in the machine, you squeeze it, and out the other side comes these long strands of spaghetti. In fact, this phenomenon is officially known as spaghettification. It's what happens to matter that's descending into a black hole. Now, black holes eat. What happens to them? Well, it turns out they get bigger. It's true with most things. You get bigger. Black holes, it turns out, get bigger in exact proportion to how much mass they have consumed. So if a black hole is of a given size and a given mass, and it eats its own mass again, the equivalent of its own mass again, then it becomes twice that size. Eats 3 times as much, it'll become 3 times that size. The arithmetic of relativity demonstrate why this is so. And again, the size is referring to the event horizon. The size of the event horizon. Well, what that means is black holes can actually be any size, depending on how hungry they've been in their lives. And not all black holes will kill you before you descend through the event horizon. Small ones will. But really, really big black holes, the tidal forces right at the event horizon are relatively low. And so they're less damaging to human biology as you descend in. So what that means is it's the low mass black holes, the ones that are the smallest, that'll do the worst damage to you as an unsuspecting visitor. It's because the rate of change of the gravity, that's the tidal force, the rate of change of the force of gravity gets significant as you near its center. In both cases, you'll get ripped apart no matter what, because there's some distance from the center where this will happen to you. The difference is that with a small black hole, it'll happen before you get to the event horizon, and everyone will get to see this happen. Whereas in a big black hole, you'll descend through the event horizon, you'll get ripped to shreds, and no one will know. Except for you. But you won't be able to tell anyone about it, of course. So now, suppose you get really, really, really big black holes. Well, let's go to the real universe. I was describing ones that might eat a person, but let's get to ones that do some real damage in the universe. In the real universe, you have stars that don't necessarily travel alone. A lot of stars that travel in pairs, call them binary stars. And when you have stars in pairs, typically one will age before the other, and part of its aging means it becomes a red giant, it swells up. And as it gets bigger, some of its material gets a little too close to the neighboring object. If the neighboring object is a black hole is going to eat it. That's not just going to eat it, it's going to fillet the red giant as it expands into its space. And we have an image of this. First, there's a person descending down into the black hole. That person is not having fun. You see the spaghettification in progress. By the way, that would happen to any material going in. It's just more explicitly conveyed when you're a human being. But notice in this image, we have a star, a red supergiant, that has become big and bulbous. And in that effort, some of its material has gotten a little too close to its companion. And that little companion is that little dot off to the left. There's a disk of material around it. That is the collection area of the red giant gas. And it feeds the material. It feeds the hole in the center. It feeds the event horizon. If we take another look at this, go close up, notice that there are jets coming out above and below. There's so much material trying to descend into that black hole. And it gets so hot because there's friction from all the gas rubbing against itself, descending down into the center. That friction heats up the gas, and that energy is trying to escape somehow. It can't escape through the plane, so it pops out the top and the bottom. And this is a classic image of a black hole with a disk of material around it, in companion with the red giant, and jets tossing, being spewed up and below, above the plane and below the plane. At those temperatures that it reaches, it starts radiating ultraviolet light, and especially X-rays. A sure giveaway of this kind of system is you look out in the universe at a star that you think is minding its own business, whip out an X-ray telescope, and that's one of the brightest objects in the sky. I mean, something's going on there. It's a disk of material, heated, coming down to a small central area. See if we have another look at that. There's the disk of material once again, but now from above the plane, you see the black hole in the center, and you just want to avoid that, really. You don't want to come anywhere near this thing. There are black holes bigger than this. These black holes are maybe 10 times the mass of the sun. And they're wreaking havoc on its neighbor star. They get bigger than this, though. There are black holes in the centers of galaxies. We know this because we've looked at galaxies of stars. We're talking about systems that have 100 billion stars. In their center is a supermassive black hole, in some cases, 1 billion times the mass of the sun. 1 billion times. They're enormous. These black holes can be can wreak such havoc on their environment that whole star clusters can get eaten. See, this black hole is so large, it has the capacity to dine on enormous gas clouds and star clusters of voracious appetite. And it too will make an accretion disk of titanic proportions. In fact, the radiation coming out of these accretion disks is so significant that, in fact, it can, on occasion, outshine the entire galaxy in which it's embedded. In fact, such objects, when they were discovered, we didn't even know what they were. We said, what is this? They emitted not only high-energy radiation, they also emitted radio waves. In fact, they were discovered using radio telescopes. And most of the energy came from a tiny little spot, not spread out like you'd see in a full galaxy. And so when these were discovered, they weren't really stars, because their energy profile didn't match that of stars. We call them quasi-stellar, the edge of the cosmos. Extraordinary. Extraordinary. Now, you know what happens? It's possible to get so big and to have your event horizon stretch out so far that no longer are you able to rip things apart, because your tidal forces are very shallow. And if you when you rip things apart, that's what makes the accretion disk. This disk of material that feeds the center. That's where the friction takes place. If you're so large and you don't get ripped apart as you descend, then you get eaten whole. You get eaten whole. If you're eaten whole, no radiation comes out. No high energy X-rays, gamma, none of that. So it's possible for a black hole to get so big that it shuts off this mechanism. We think some quasars that have turned off since the beginning of time have done just that. By the way, there's another way to turn off, and that's if you've eaten everything in your environment and nothing comes close to you anymore. That's another way to turn off. You just ran out of food. Well, the latest evidence suggests that perhaps all galaxies have black holes in their centers. Some more massive than others. Some galaxies that have supermassive black holes, if those black holes are kind of quiet, we suspect that those galaxies in the distant past would have looked to us like quasars. So it's a shift in paradigm of how we think of galaxies in modern times. When I first started school, it was, well, there's this kind of galaxy, and there's that kind of galaxy, and there's a quasar, and that. It's all the same kind of galaxy, just slightly different properties within it. It's not a different species. They're all the same species, just with different mass of the black hole in the center, slightly different rotation rates. And by bringing them all together in one intellectual construct, it enables you to more thoroughly examine how it is that these objects differ. Because you're already grabbing onto a core of what is the same. The fact is they're all galaxies. Milky Way, our galaxy, of course, it's got a black hole too. No, it's not as big as the biggest. It's not as, but it's kind of like an ordinary black hole. Our black hole, if you have black hole envy, all right, our black hole is about 1 million times the mass of the sun. Turns out that's not big enough to have ever really looked like a quasar in the early times. But it is big enough to kind of disturb the middle of the galaxy. And the colleagues of mine, whose entire research program focuses on exactly what's going on in the center of the galaxy. You track the motion of stars that get almost too close to the black hole. The gravity is so high, they get pulled in very fast. You see stars kind of minding their own business, and then whew, they come a little too close to the black hole, and you see their speed increase dramatically, speeds that you don't find anywhere else in the galaxy. That tells you that there's a lot of mass in a small volume. These are some of the ways we have deduced that every galaxy we've ever looked at has evidence for a black hole in its center. So black holes, they're things to respect in the cosmos. And I'd like to summarize their danger with just a rhyme. I suffer through this rhyme that I once composed because I felt compelled to do this. Because black holes, I couldn't get black holes out of my head. And it goes something like this. In a feet-first dive to this cosmic abyss, you will not survive because you surely will not miss. The tidal forces of gravity will create quite a calamity when you're stretched head to toe. Are you sure you want to go? Your body's atoms, you'll see them, will enter one by one. The singularity will eat them. And of course, you won't be having fun.